All right, class. Welcome once again. Basically, I want to capture the second makeup lecture today. And what I wanted to do was similar to our previous lecture, I wanted to discuss some of the theory behind nonlinear programming. In the previous lecture, we talked about IP, and so today the focus will be on NLP. So with that, I'm going to bring up a couple of slides here to provide you some additional background. So when we talked about LP problems using solver and using the simplex method, pretty much if we did the formulation correctly, we would get an optimal solution. However, when we talk about NLP problems, the answer is not so straightforward at times. And by way of example, I'll show you exactly what I'm talking about. So continuing, so the basic idea of nonlinear, so if we had a nonlinear function as displayed here, depending on where I started to conduct my optimization, would give me a varying response. So what I mean by that is if I started, for instance, in this function at point B, then my optimum solution, depending on how I structure the problem in solver, would give me point C. Now, point C, if we're looking at the overall function, point C would be considered what's called a local maxima, right? So if we were to plot this whole function as you see here, it would be a local maxima, but not the global maxima, which would be represented by point A. So problem has this issue where if it's not configured correctly, it could give you not the optimal solution. I don't want to say the incorrect solution. It'll still give you a feasible solution, but not the optimal solution. Okay. So to dissect this further, obviously the difference between simplex and NLP, simplex is guaranteed to find you an optimal solution on one of the corner points of the feasible zone, where in NLP, any single point within that feasible zone has the opportunity to be an optimal solution. So that really introduces a little bit more complexity in terms of searching and defining what the overall global maxima or optimal solution is for the entire NLP function. Diving in a little bit deeper, when we talk about nonlinear functions, it really comes in a couple of what I call flavors. The first one is what's called a convex function. So looking at the plot here, really what we have is the rate of change, or the slope of the function, is always what we say non-decreasing, or it is an increasing function. So if we were to draw a line on any 2 points of the function, as you see here, that line would lie above what we call the curve. Okay, so that's indicative of a convex function. On the flip side, if we look at concave, and one way that I learned, at least when I was growing up and going to school, was obviously concave. It looks like a cave, right? So that's kind of what's being illustrated here. In this case, the slope is non-increasing, or it's a decreasing function, the way the slope is being represented here. And similar to a convex, if I was to plot a line and connect any 2 points on the function, the line would be below the curve, as you see in both examples. Okay, so that's indicative of a concave function. All right, and there's different rules and assumptions that we can apply. For instance, if we were to add up different convex functions, the result of the summation of those concave functions the summation of convex functions is convex, and the sum of concave functions is concave. So in other words, if we were to apply the additive property here for these different types of functions, the basic nature of that function would not change if we would add them together. And other assumptions that would hold, if you were to take any convex function and multiply it by any positive constant, the function would still remain convex. And on the flip side, same thing with concave. If we were to multiply that by a positive, it would remain concave. And lastly, if you were to multiply convex by a negative, then we would have the opposite effect, and it would result in a concave function. And last but not least, if we were to multiply any concave function, once again with a decreasing slope, by any type of, or any negative constant, then it would shift from a concave function and convert that to a convex function. So once again, a few rules of thumb to keep in mind. All right. In certain conditions, once again, depending on whether it's a concave or convex function, you are guaranteed to find the global optimum of a nonlinear model. Okay, so for instance, if we're looking at max problems, where the objective function is maximization, if that's the case, then if we're looking to find the global optima, then two conditions have to be met, as it's mentioned right here. First of all, the objective function is concave. Okay, the objective function is concave, and the constraints are linear. Or we have a minimization problem where the objective function is convex, okay, and the constraints are linear. And if you were to plot that, it would make a lot of sense. And really what you're doing is you're looking at the direction of the curve. Once again, if we're trying to maximize or minimize, right? Here we'd go to the lowest point for minimization, and here if we're looking at a max problem, we go to the max point here on the curve. Okay, so a couple of conditions have to hold to find an optimal solution, a global optima. If certain conditions do not apply, then consequently we would not be able to verify a global optima. And in that case, what actions can we take? That's really the question. And if we have certain situations that do not hold to these assumptions, right, which is quite possible, then what do we do? Well, in that case, it's not so obvious. We can try different starting points. For our changing cells, it's a little different. We'd try different starting points. So instead of setting it to 0, we can set it to some certain value, maybe possibly over a range of values, and see what results we get. And if basically we run it several times, and the overall solution does not change, then we can be somewhat confident that we've arrived at the optimal solution, or best yet, just trial and error. And try different selections for your changing variables, and whatever yields the highest value, then that would be your optimal solution. Once again, it's not ideal, so we have different ways to kind of basically apply methods within Solver that can remedy the situation. Okay, and obviously, once again, even if you're not sure about the optimal solution, we can always try different combinations, but that makes it kind of difficult. And so what Solver provides is what's called a multi-start option. Okay, and what that does is it basically allows your changing variables to start at different values. Okay, random starts, and so basically it will look at a nonlinear function, and if it has local optima, it will evaluate those local optima by starting the function at varying values across the board that are within the bounds of that function, it will evaluate the local optima, and from that it will be able to determine if that local optima is indeed the global optima. So we have in Solver what's called this multi-start option, which really resolves and takes away the headache of trying to do it the trial and error method, which can be quite tedious and time consuming and inefficient. So surely some benefits of using this particular option. So if you run into a problem that you're working on either in this class or outside this class, and you're having issues in terms of, well, specifically with the nonlinear function, make sure that you have this multi-start selection within the properties or settings of Solver selected. If I can just show you a quick example of what I'm talking about, let me just pull up this Excel file real quick. And so basically what we have here, class, is we have this function, as you see here, nonlinear function. We see it plotted here, and the values, the x values, range from 1 to 5. Okay, now what I'm going to try, and you see, obviously we have different local optimas here, especially at this point and this point. This would obviously, we can look and determine that that's actually the global optima. But let me just show you some of the issues that we can encounter. I just want to check the, and once again we're using the GRG nonlinear. We have the two constraints where obviously our value decision variable has to be less than 5 and greater than 1. So this is our range of values for our decision variable. I just want to click here on options real quick. So right now, if I click on the GRG nonlinear tab, I'm using multi-start. So I'm going to take that off for a second. So I'm not using the multi-start. Close out of this, and I am going to start, let's just say, so this is my changing variable. So I mentioned, like, at different starting points I might get different results without the multi-start. So let's just say I type in 3 here. Okay, and this is essentially just taking the product of all these values. So basically it's encapsulating this nonlinear function, as you see. It's calculating right here, and this is basically doing a sensitivity analysis. But anyways, I want to go back to Solver, and I want to solve this once again without the multi-start selected, starting at point 3 on the nonlinear function, and I hit solve. Okay, and if I hit OK here, what you'll see is the x value, the optimum solution that yielded was 3.54, which is essentially like this point right here along the x-axis. Okay, along the x-axis, it basically determined that my optimal solution is where x is 3.54, which is essentially like right there. And we can check down here and look at the sensitivity. Obviously the precision isn't on par with what we have here. So just looking at that, we know, well, hey, that's obviously not, that's a local optima, but it's not the global optima. So what we can do is go back to Solver, go back to the options, once again click on GRG nonlinear tab, and select use multi-start. So basically, once again, it's just randomly selecting values within this range and testing them in an automated fashion to give you the optimal solution. So if I click there, okay, and actually what I want to do just to compare apples to apples is I want to type in 3 here again like I did last time. Okay, when I solved it. So the only difference is I have multi-start selected in options. Everything else stays the same. I hit solve now. And, excuse me, and now you'll see that the solution is 1.355, so that corresponds to this point right here. So in other words, using that multi-start option in Solver, I was able to calculate the global optima of the nonlinear function. So with that, class, I am going to wrap this short lecture up. As an assignment for this lecture, basically I want you to tell me the difference between a local optima and the global optima, and what we can do in Solver to ensure that we identify the global optima. of the nonlinear function. Okay, so that's going to be the assignment attached. And once again, I believe you can probably solve this in 2 or 3 sentences, so it should not take too much of your time. Once again, thanks for tuning in, and I will catch you tomorrow.